It's science, but not as you know it. The Naked Scientists.
Hello and Happy New Year. This is The Naked Scientists with Chris Smith and Kat Arney. Coming up on today's show, we'll be finding out how smoking alters the structure of teenagers' brains. Apparently it can make you much easier to distract, and we'll be finding out why. Also why a bad night's sleep might be linked to diabetes, and also how researchers have used gene therapy to treat alcoholic rats. That's all on the way.
And also this week we are looking at the science of addiction. Why do we get hooked on things? What's going on in our brain when we develop an addiction? What is the best way to stop it? Also, unrelated, in this week's Question of the Week, we're trying to untangle possibly the biggest mystery on Earth.
I would put my MP3 player into a pocket, and every single time I pull it out, the wires are completely tangled up. In fact, they're so tangled, I couldn't even do it myself. My question is, why do wires get tangled?
It is irritating. I cannot wait to find out why. And interestingly, the key to keeping your cables tidy also applies to your DNA, as we'll hear later. And also, if you've gained a few unwanted inches around your middle over Christmas, as we all do, we're going to be talking with diet specialist Dr. Tony Steer to find out how to avoid some of those common dietary pitfalls.
Thank you, Kat. So if you've got a science question for us for 2008 about the science of addiction, or perhaps even kicking the habit, then do get in touch. Email chris@thenakedscientists.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's take a look first off, as we always do, at what's been hot in the world of science news over the Christmas and New Year period. And there's a very interesting story here, Kat, which is that scientists have found that a good night's sleep, or lack of it, could be linked to diabetes. And that's because Ezra Tassali and her colleagues there at the University of Chicago Medical Center studied 9 healthy volunteers, and they disturbed their sleep over 3 days. So what they did was to monitor their brain waves, and whenever the computer sensed that they were going into a phase of sleep called deep sleep, and this is characterized by a certain pattern of brainwaves called slow wave sleep, they played a sound through a speaker, which was just loud enough to arouse their brain a little bit. So they went out of slow wave sleep and into a less deep sleep, but not enough to physically wake the subjects up. And after each of the trials, they then gave them a challenge with a small injection of glucose, just sugar. And they then monitored their glucose levels and their insulin levels, the hormone that brings sugar down in the bloodstream and which people with diabetes don't have enough of. And they were really surprised to see that at the end of the study, in 8 of the 9 subjects, their level of sensitivity to insulin was 25% lower. And so, in other words, when they injected the glucose, it went up 25% higher than it should be, and then stayed there, and it took much longer for it to come down again, and they didn't have enough insulin. And so it looks like this slow wave sleep is very important in producing the right amount of insulin in the body, and so sleep could be linked to diabetes, and therefore people who don't get a good night's sleep, that could be one of the reasons why people get diabetes, or it aggravates the situation, because commonly we say obesity is linked to it.
Because that could be kind of a double whammy, because you have the effects of obesity on your blood hormones, but then also people who are very overweight do have this problem with sleep apnea. They can basically cut off their air supply during the night, so that might be stopping them getting a good night's sleep. It's very interesting.
That's what they're arguing, that people who are elderly don't sleep very much, and they're more prone to type 2 diabetes, and people who are obese, as you say, don't get a very good night's sleep for the reasons you outline. And for exactly that reason, it could be that that's why they have a lower amount of insulin than they need. They're insulin insensitive, and this is aggravating the onset of diabetes. As Ezra Tassali says herself, we were giving these subjects the sleep of someone in their 60s, despite the fact that they were only in their 20s.
Did they find out if they were a bit grumpy afterwards?
I think they probably would get out of bed on the wrong side after that.
But anyway, if you've overindulged at the bar this festive season, of course not like us at The Naked Scientists, as sober as judges, you might be interested in the latest research from Professor Yedi Israel and his colleagues. And they've managed to develop a type of gene therapy that can cut long-term drinking. But the problem is that this only works if you're a rat. Now, the treatment's based on a gene for aldehyde dehydrogenase, and this is an enzyme that helps the body to break down alcohol. And in fact, some people who are from East Asia, they actually have a faulty version of this gene, so they can't really break down alcohol properly, and they get sick, they get flushed, and they have a pounding heart after just a couple of drinks. But this gene therapy for rats, it works by injecting what's known as an antisense version of the hydrogenase gene into the blood, and then it interferes with the normal activity of this enzyme. So you can't make the enzyme properly, and then the toxic byproducts of alcohol build up and cause pretty nasty effects. Now, the researchers tested this on rats that had been basically bred to be heavy boozers, and were also fed the equivalent of rat lager. I don't quite know what rat lager is, but anyway, after a single injection...
Did they get ratted?
They may have got ratted, yes, Chris, well done. After a single injection of the gene therapy, the treated rats cut their alcohol consumption voluntarily by about half for at least a month. I mean, it didn't make them totally teetotal, but they did voluntarily cut down quite significantly. I mean, this is only an experiment in rats, so we're not going to be going around, hovering around the pubs injecting people quite yet, but it's certainly interesting.
Do they actually understand why the rats were motivated to cut down their drinking when they knocked off the action of this enzyme? Was it just that the alcohol they did have in them persisted for so long that they just had very high levels already and they were sort of chronically high in alcohol, which staved off their addiction anyway?
Possibly. I don't know the exact mechanism. Maybe it just made them feel crappy, or maybe they just felt drunk all the time. Who knows?
We're talking about interesting things that have happened as well. That, hurricanes are a major problem in world geography, world geology, that kind of stuff. And there's a really interesting piece of research which has been done by a couple of guys, and they're based at the NASA Goddard Flight Space Center. And what they were doing was wondering whether ocean temperatures can be manipulated by dust that's blown off of the Sahara Desert. Because if you look at the Sahara Desert, it's a massive source of dust that gets blown off of the desert, 200 million tonnes on average every single year into the atmosphere. That's as much dust as
under my bed.
Nearly as much. I've seen your bedroom. Terrible. But this dust takes to the air, and the researchers wondered whether it could act as a sort of shield reflecting sunlight that can warm the ocean and drive hurricanes back into space. Because where hurricanes are spawned, it's in the Caribbean Sea and in the Western Atlantic near the Caribbean. When you have sustained high ocean temperatures of something like 80 degrees for a period of time, the warm ocean water warms up the air above the ocean, and this causes rising air currents which slowly gather speed and pull in cold air to replace the rising warm air. And because the Earth's spinning, the air that comes in to replace the warm air is also spinning, and this starts the vortex of a cyclone. And so what they wondered was, if you cool down the ocean with this dust cloud, does this translate into fewer hurricanes? So they did some simple studies. They looked at sea temperatures in 2005. They looked at the size, using satellite images, of this dust cloud that was up there, using the satellites to look down, and they found that in 2006 there was a bigger than average dust cloud, lower than average sea temperatures, and therefore fewer hurricanes. And in 2006 no hurricanes actually made landfall. None of them reached the land. So it does look like a reasonable way of predicting the intensity in late summer of the forthcoming hurricane season, to the extent that a number of climate modellers and longer range weather forecasters, including a group at Colorado State University, are going to start embracing these measures and putting them into their prediction models.
Hey, it does make you wonder if you could prevent hurricanes by going and chucking a load of dust over the sea. That might...
Well, you'd have to actually have to put it up into the atmosphere at a level where it could reflect it back into space, and also obviously not compromise human health. We don't have a choice over whether the dust comes off the Sahara. It's going to happen anyway. We can't possibly control for that 200 million tonnes of Saharan sand. But if you started ejecting stuff into the atmosphere, that could be a problem environmentally, couldn't it? Yeah,
I can imagine, the problems of trying to seed clouds and things like that. Anyway, a completely unrelated story, but a new survey of 200 doctors in Chicago has shown that nearly half of them have actually given patients a placebo, that's a dummy treatment, at some point. Now, nowadays we usually think of placebos as being something that you use in clinical trials to compare, your genuine treatment with the effects of a placebo. But actually, doctors in the past used to use placebos to work out if a patient was really ill or if they were actually faking it. But in fact, now we know more about the psychological basis of some illnesses and the placebo effect, which is really quite pronounced. It seems that some doctors nowadays are actually believing that dummy treatments might have some benefit, even if it's only psychosomatic.
There's a big problem over the ethics, though, isn't there? Because if I were to do that, and I'm not saying I have or I haven't, if I were to do that on patients and they then said, why did you tell me I was having a drug when I wasn't? You've effectively lied to me. I could actually be disciplined.
Yeah, exactly. It's a really interesting ethical challenge, and it's something that's been very hotly debated. And in this survey, around 1 in 10 doctors said that they thought placebos should never be used. So the majority thought that it was acceptable to use placebos. And some of the doctors who gave placebo treatments, they used various terms to say what they were giving. For example, this is a substance that may help and will not hurt you. This is medication. It is a medicine with no specific effect. So they were saying all sorts of things. But there is obviously this big moral dilemma. And we know that placebos can have effect. I mean, it's not called the placebo effect for nothing. It's about sort of 30% improvement. But there are very big issues over the ethics of it, but there is clearly growing interest in the connection between mind and body, and it's something that really needs debating, I think.
Maybe patients need to have it pointed out to them when they go to hospital that you may be given a placebo, or you may not, and then they're aware that this may be a therapy, because we know that it does have a benefit, and we know that people do derive benefits from it, and so therefore it might be worth trying. If there's no drug that could definitely make you better, it might be worth trying.
You could try homeopathy instead, I suppose.
Well, you were talking about Harvard. I'm very quickly going to talk about a study from Harvard which has been done by Shakira Franco-Suglia, who's at Harvard. She studied 200 children around the streets of Boston and compared their exposure to traffic pollution with their IQ. And the really interesting result was that after controlling for socio-economic factors, so social class, people living, if they're poorer, closer to busier streets, for example, even after controlling for all that kind of thing, they found that those who were exposed to the most traffic pollution had, on average, 3 IQ points lower scores on verbal reasoning and IQ tests than on children who are their cleaner breathing counterparts. They don't know the exact reason why this has been found, but they put it down potentially to particulates, because lead was banned in fuel for the very reason that it causes a mental decrement and it can affect the brain developmentally. But this effect is equivalent, every bit as equivalent as the effect of lead, if you look at it. So it's quite a powerful effect. What could it be? Well, if it is these particulates, how are they affecting things? Well, studies in animals have shown that they can trigger bits of inflammation in the brain, so it might be that perhaps they're penetrating the nervous system and causing brain cells to die, or causing low-grade inflammation in the nervous system. There is evidence that they can gain access both through the lungs, but also via the olfactory system. So you breathe in these particles and they can go along the nerve which runs from the nose into the brain, and perhaps deliver these particles to the temporal lobes, the lower part of the brain. And the evidence that this can happen is that when someone looked at dogs living in Mexico City, they found that dogs that were living in the most polluted bits of Mexico City were much more likely to have Alzheimer-like changes in their brain, so literally brain degeneration, compared with dogs that were in cleaner parts of the city. So it looks like pollution can translate, especially if you're living a very unclean, polluted life, into a lower amount of IQ. So the evidence is go and move to the countryside where the air's cleaner, if you can.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
Now, we've been talking about things that can become addictive, and we'll be talking later with Barry Everett about what actually physically is going on in the brain with addiction and how to kick the habit. But one addiction that's probably the most common on earth is the addiction to cigarettes, so tobacco, nicotine addiction. And there's a very interesting study which has been done by Professor Leslie Jacobson. She's at Yale University School of Medicine, looking at how smoking affects the brains of teenagers. Hello, Leslie.
Hello.
Thank you for joining us on The Naked Scientist. What have you found?
Well, we studied 67 teenagers in this group and found that the children or the teenagers who smoked, relative to those who didn't smoke, actually had a decline in attention, in particular auditory attention, and at the same time had abnormalities in the structure of their brain that looked like actually premature developmental changes. And the reason why this intrigued us is that, in fact, nicotine in tobacco smoke binds to a receptor called the nicotinic acetylcholine receptor that's very important in modulating development in both prenatal and adolescent life.
So you can actually place the receptor for nicotine, the part of the brain it affects, at the part of the brain you're seeing changes in at this phase in the teenager's development.
Right. Well, the receptor is actually very widely present in the brain. It's all over, but we do know from research in rats, in particular by Dr. Methurate at the University of California in Irvine, that nicotine can alter the normal development of parts of the brain that support auditory attention. This is very intriguing to us because nicotine exposure during prenatal development leads to a greater risk of impairment in auditory attention and attention deficit hyperactivity disorder. So we actually feel that these findings may show us how this may be happening, at least in some children.
How did you actually make the discovery in the first place?
We first recruited teenagers who smoked and those who didn't, and interviewed the mothers of the teenagers as to whether they smoked during the pregnancy, and we also obtained birth records to verify the mothers' reports. Then we tested them in a special test that looked at auditory and visual attention, and then obtained some MRI scans, which is basically taking a picture with a very strong magnet of the brain. And we can measure both structure and the maturation of white matter, as well as blood flow linked to cognitive work, like paying attention to a task or listening carefully in the presence of distractors.
And this showed that the children that had either been prenatally, so when their mother was pregnant, exposed to smoking, or as teenagers were exposed to smoking, had a greater degree of distractibility. It was easier for them to be put off from a task that they were doing when you had some kind of auditory stimulus, some noise or something.
Exactly, and the effects were most pronounced when kids were exposed prenatally and during adolescence.
And what about in adults, Leslie?
Are you asking whether it reverses during adulthood?
Well, I guess, yeah, because what we want to know is, do a lot of people take up smoking when they're in their teenage years?
Right.
Do they still continue to suffer from these problems into adulthood, or do they get better, or do you not yet know that?
We don't specifically know that. It's likely that stopping smoking would improve attention. I think it's worth a try. However, what we do know is that acutely when you stop, you go through nicotine withdrawal, and that's very hard on attention. So if you're already having a deficit in attention and it gets worse during the first few days or weeks of stopping smoking, then I think there's even more pressure to relapse to smoking, if you follow what I'm saying. In other words, this deficit may make it actually harder to quit.
And you don't think that the people in your study, when they're in the brain scanner, were feeling a bit nicotine deprived, and this was putting them off from doing the trial properly, because normally they would have been smoking?
We actually studied the smokers. We didn't actually ask them to stop smoking for this study, and they often took a smoke break right before they had their scan. We measured their nicotine plasma concentrations, and they were very much in a stable area that was consistent with smoking, so they were not in nicotine withdrawal.
So where are you going to take this next?
Well, the next question I think we have here is whether we can measure changes early after prenatal exposure. So we're working to develop a study that will recruit infants with and without exposure, look at brain structure using the MRI scanner, which is very safe, and then follow them prospectively. And the idea here is to identify what infants are affected, and then, of course, whether we can develop therapies that will improve their attention and reduce their risk of smoking and other like problems that come from inattention, like school failure.
Well, let's hope that it isn't permanent. Leslie, thank you very much.
My pleasure.
That's Professor Leslie Jacobson. She's from Yale University School of Medicine and has found that people who are exposed to nicotine, as their mother smoking, for instance, when they're in the womb, or as a teenager, can have consequences for the structure of their brain as they get older.
Scary stuff. And if your New Year's resolution was to give up smoking, it's not too late to start. It's never too late to give up smoking. And if you do want help with that, the best thing to do is to go to your GP, and they can put you in touch with the NHS Stop Smoking Services. Best way to give up. Anyway, now let's go over to Ben for the first part of this week's rather squid-tastic Kitchen Science.
Hello, welcome to Kitchen Science. Today we've come to Stewart School in Harlow, and we've got a bunch of volunteers here to do some science experiments with us. I also, of course, have Dave Ansell. Hi, Dave.
Hi, Ben.
What have we got lined up? What sort of experiments?
We're going to be trying to levitate some plastic bag using just a balloon.
The volunteers we have helping us today are Jai and Jack. Say hello, lads.
Hello. Hello.
What year are you in?
7.
And what do you think of science in school?
Great. Excellent.
Good, good. And do you enjoy the experiments, or do you just enjoy learning about stuff?
Both. I prefer learning, but I do like both as well.
Do you think it's going to be possible to make a plastic bag float using a balloon?
Maybe, because of static electricity.
So how do you think that might work?
No idea.
So they think it's something to do with static electricity. What do we have to do to test this out?
Well, for this, you want a balloon, ideally one of the long, thin ones, a little piece of plastic bag, maybe about 1 centimetre wide and 4 centimetres long.
So not a whole plastic bag, then?
Not a whole plastic bag, just a little bit of one, a pair of scissors and some nice hair to rub the balloon on. So firstly, Jai, could you come over here and chop a piece about 1 centimetre wide and 4 centimetres long from the plastic bag?
I'm cutting one piece and then I'm leaving at least 1 centimetre gap and cutting some more, and the pieces come off.
Great. OK, Dave, so we have this plastic bag tag now. Now what do we do with it?
OK, Jack, could you get that tag and then slice along it into lots of thin strips, about 1 millimetre wide, but not quite chopping them off. So they're all held together at the end with a little tiny narrow strip.
So it becomes a sort of tassel rather than a tag.
That's the idea, trying to turn the tag into a tassel.
Jack, how are you doing that?
Fine.
You want to get the strips in the tassel as narrow as possible. It works better that way.
OK, Jack, you done?
Yep.
And what does it look like?
Bit of jellyfish or something.
It does look like a jellyfish, kind of like a squid. OK, so we'll call this our plastic squid. Dave, what's the next stage?
OK, next you're obviously going to have to blow up a balloon, so I'm going to give one each to Jack and Jay.
Dave, they're struggling to blow up those balloons. Any advice for blowing up balloons at home?
It generally helps you stretch them to start with, and the first part's always the hardest, so just try really hard at the beginning, and it should be able to inflate them. OK, once you've got that balloon blown up, you should tie it off, and then you've got like a balloon baton shape.
So now we each have a plastic bag squid and a blown-up sausage-shaped balloon.
OK, so if you want to try this at home, the next thing to do is to rub both of them on your hair, charge them up really well. When you're rubbing the balloon, just rub one side of it and remember which side you've rubbed. Then throw the squid up into the air and hold the balloon with the bit you rubbed pointing upwards and try and balance the squid on top of it.
So you rub both the balloon and the squid on your hair?
Yeah, ideally different bits of the hair, it'll work better that way.
OK, well, we're going to do this here at Steward's School, and we hope you're going to try it out at home, but we will come back to you later on in the show to let you know what happens.
Hilarious. So, all of you at home rubbing plastic bags on your hair, do let us know how you get on. If you've got a balloon and a spare plastic bag, do try this. Let us know what happens. Email chris@thenakedscientist.com.
Peter in Colchester got in touch, Kat. He said he'd be very upset if he'd paid a prescription charge for a placebo. It's a very good point, isn't it? That prescription's not cheap, and if you're being sold nothing but water, that's a bit dodgy. He also says if it doesn't work and an illness worsens, would the doctor be liable? Another good point, because I think effectively you would only be able to give the placebo as a last-ditch thing, or as an add-on to something which you knew could work, or if there was nothing to offer, for example.
Exactly.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
You are listening to The Naked Scientist, here with Dr. Chris and Dr. Kat, and we are talking about the science of addiction. And we're joined in the studio by Professor Barry Everett, who's Professor of Behavioural Neuroscience here at Cambridge University. Good evening, Barry.
Good evening.
How are you doing?
Fine, thank you.
Excellent. Now, we're going to start by talking about what is addiction. What does it mean when we talk about someone is addicted to something?
Well, I think the easiest way to think about an individual who's addicted is someone who compulsively uses drugs, seeks and uses drugs at the expense of other activities, and finds it impossible to relinquish that drug-seeking, drug-taking habit. So I think the essence of addiction is compulsive or out-of-control use, which really differentiates it from the kind of drug-taking that many people do at some point in their lives, where they take drugs to, like cigarettes. It's easier to think about cigarettes or alcohol. You smoke and you may drink to experience the effects of the compounds in tobacco smoke and alcohol itself. And having done that, some individuals are vulnerable to those effects, and they go on to keep using and using and using, and they lose control over that use and gradually progress to the stage that we can think of as addiction.
And what's going on in the brain when someone's, say, becoming an addict to drugs or to alcohol? What sort of changes are going on there?
Well, very complex changes. So for many years, research in this area has focused on what might be the mechanism that mediates the effects of drugs, and it's in this context that a particular chemical messenger in the brain, dopamine, has been implicated. And it seems that many drugs from different classes, nicotine, cocaine, heroin, alcohol, all individually very different drugs, all have this ability to increase dopamine in particular parts of the brain, and this may be a key element of why the drugs are initially positive in terms of their effects, but that doesn't explain the progression to a more compulsive form of drug use, and this really moves beyond the realms of a simple chemical messenger system to encompass adaptations to the chronic taking of the drug in many parts of the brain.
So what is it? Why can one person have a drink and that's fine, and someone else will become an alcoholic if it's all the same systems?
Well, that's the key question, and so we tend to talk about here vulnerability, and vulnerability is undoubtedly in part genetically determined, and there's been some progression in understanding what vulnerability means.
So we're talking about an addictive personality, basically?
Well, yes, but not in the sense that addicts are simply born and not made. So this isn't a single gene type of disorder. It's a behavioural trait that's under the regulation of many different genes, and we know about one of those traits in particular from quite recent research, which is that individuals who have an impulsive trait or an impulsive tendency, in other words, they respond rather too quickly and without sampling the environment, tend, if they're given exposure to drugs, not simply to take them more readily, but to escalate their intake. And having escalated their intake, they then undergo a series of adaptations to the brain which sees them progress into compulsive use so that they can't stop.
So that's the sort of thing. There's a slight thing I want to digress onto, which is that some people can become addicted to chemical things like drugs and alcohol, and some people seem to be addicted to physical behaviours. Chris, you've got some examples here.
Got an email here from Sam McKee. He says, I'm a high school teacher and music teacher in Brisbane, Australia. I really enjoy listening to the podcast version of your programme whilst I'm having a cup of tea or coffee. Therein lies the clue. About a month ago, I decided to cut back on my caffeine intake and decided to quit cold turkey. Unfortunately, it was a school day, and by lunchtime I had a splitting headache and I was very moody. My students asked me why I was a bit grumpy, and they convinced me to have a cup of coffee at lunchtime and to give up coffee during the holidays. What's actually happening to cause this?
Well, what happens, if you're going to have an addiction, this isn't a bad one to have because it's A, quite trivial, and B, quite easy to relinquish. But what happens with people who drink coffee very frequently is that they develop tolerance to the caffeine that's in the coffee. And as they develop tolerance to the caffeine, when the caffeine isn't there, they experience discomfort in the form of withdrawal, which can be things like a headache, and it can be also maybe minor mood changes, but sometimes even things like palpitations that come with withdrawal from caffeine. And so you then take more caffeine, and you have to do that more and more frequently until eventually you have a situation in which people are drinking vast quantities of coffee and caffeine or tea and caffeine during the day. And so then when they suddenly stop and decide to go cold turkey, often happens to people on weekends, actually, when they take coffee during the week to stay active at work, and then at the weekend they tend to take less and they have headaches and they feel bad. But if you just stay with that withdrawal symptom for a couple of days, it disappears.
But not with heroin, presumably?
Well, with heroin there's also a physical withdrawal syndrome, which a major theory of addiction says individuals will take heroin not so much to get the positive effects of the drug, but to stop feeling so bad when you're in a state of withdrawal. But that's neither necessary nor sufficient to actually explain the compulsive use of heroin. And many addicts will use heroin over a long period of time without ever undergoing withdrawal. So withdrawal illness is not a necessary and sufficient condition for addiction.
And very, very briefly, what about people who can get addicted to physical behaviours and these kind of things? We had someone who says they think they're addicted to internet porn. You know, is that the same kind of mechanisms going on as well?
Well, who knows whether there are any mechanisms that are the same that are going on. But I think to some extent there's an issue of semantics here. And maybe it's easier to think in terms of, again, of compulsive use, that individuals may engage in behaviours that they find it difficult to relinquish. And so you could describe that as being addicted. I would prefer to say that they were compulsive visitors to internet porn sites and were doing that rather than were going to undergo some state of withdrawal or whatever if they didn't have access.
Barry, why has the brain got a system in it that lets us get addicted to things? It seems like such a bad thing to have, because we've outlined a few bad examples. Why should we have that wiring?
Well, it isn't there so that you get addicted. It's presumably there because You need a mechanism in the brain that mediates the positive effects of natural goals and rewards, like food and drink and social rewards and affective systems. And like any system in the brain, it consists of groups of neurons that talk to each other, and they have chemical messengers. And the chemical messengers in this system happen to be ones that are potently affected by drugs that are taken. And so you get a kind of a super hit on those neurochemical systems, which is probably, at least early on, a part of the mechanism that causes you to seek that hit again and again.
This is probably a very good time to introduce our other guest, Barry, and that's Julie Cower. She's from Brown University in the US, and she's been working on some of these mechanisms. Hello, Julie.
Hi.
Now, you've been studying actually some of the connections that happen in the brain. Tell us what you found.
Well, let's see. Briefly, there's been a growing theory in the field of people who study cellular changes that occur during addiction, that the changes that occur in the brain are somewhat akin to those that occur with learning and memory. And so over the last 10 years or so, there's been a growing number of research papers looking at this problem and trying to see whether or not indeed, the changes that occur in parts of the brain involved in, say, dopaminergic function, as Barry was just mentioning, may be similar to those that happen in parts of the brain involved in learning and memory.
So in the same way as you learn your maths homework or something, you also learn to take drugs?
Well,
so what's the reward then in doing your maths homework versus the reward you get for taking drugs? Because drugs temporarily can change your mood, and that's the attraction to most people of using them. Whereas learning a memory, we know what's the reward.
It's a little more complicated than that. So it's a more basic mechanism that is similar between the two processes. It's not simply a learning to be addicted to a drug because it's rewarding, whereas you may not find math to be as rewarding. Instead, the changes that occur during learning are a strengthening of the synapses, which is the connection between two neurons. And there's considerable evidence that during learning, what happens is that the synapses, the connections between cells, become stronger in parts of the brain that subserve memory. However, in the parts of the brain that subserve addiction, and as Barry mentioned before, the reinforcement to natural rewarding stimuli and things that are important for survival, the strengthening of those synapses that occurs by drugs of abuse may have pathological effects on the system that actually directly tap into long-lasting maladaptive changes in that circuitry. So it's not that the same circuits that you're learning with during your math homework are altered during your use of cocaine, but rather it's a different part of the brain in which maybe these changes in synaptic strength are not appropriate and are perhaps even beyond what should normally happen with normally rewarding stimuli.
So when we learn something, you have a connection between nerve cell A and nerve cell B, and that connection can be strengthened or weakened, and that's the learning experience. So how are you proposing that drugs of abuse, addictive drugs, can affect that process? What's going on?
Well, we found two things. So first of all, there's considerable evidence. So the neurons that release dopamine, which seem to play a key role in early responses to drugs, certainly. Those neurons can be controlled by excitatory inputs onto them or inhibitory inputs onto them. And there's a lot of evidence that a single exposure to a drug of abuse, and this seems to be multiple drugs from ethanol from alcohol, that is, to cocaine, all produce a strengthening of the excitatory synapses, which then would drive those dopamine neurons to fire more frequently and for long periods of time, which may contribute to the early effects of drugs. The other way that you could increase the firing and activity of dopamine neurons would be to reduce inhibitory inputs onto them. And what my lab found was that a normal process that seems to occur is potentiating of those inhibitory circuits. And this may exist as a way to sort of balance the potentiation of excitatory synapses in the normal, healthy brain. But what we found, intriguingly, was that if an animal was given morphine and then we looked 24 hours later, we found that this inhibitory potentiation was completely absent.
So does this mean that potentially one exposure to one of these nasty agents could have lifelong consequences?
I don't know the answer to that question, and we're very interested in finding it out. Clearly, the work that my lab's been interested in can only really speak to initial effects of drugs, and very clearly, in most cases, a single exposure to one of these drugs does not produce addiction. However, it's possible that taking the drug even once sets the stage in a way for the vulnerability issues.
And just very briefly to finish off, Julie, given that you found this new mechanism, or you're uncovering this new way of thinking about how addiction occurs, you've therefore got now another way to think about how to break an addiction. Could we block this process and therefore treat people who have an addiction to various drugs via a new way?
Well, the work that we have carried out has pinpointed a single molecule in this dopaminergic brain region called guanylate cyclase. And what may be true is that if we were to modulate this drug target at the same time that an addictive drug like morphine were delivered to a person, that we might be able to ameliorate any addictive properties of the drug that would develop over time without affecting its analgesic effects. And as morphine is given frequently in the hospital all the time, this might be a useful process. We don't know whether or not targeting this molecule, however, would be able to reverse addiction, which is, clearly a very persistent problem.
It still sounds like a very fertile area to look into. Julie, thank you very much. That's Professor Julie Cowes. She's from Brown University. And if I could just come back to you very briefly, Barry. Connie in Manchester got in touch and said, is it true that if serotonin levels are down, people are more likely to tend towards addiction? So can specific foods, if you eat them, put up your serotonin levels and therefore stave off that effect?
Oh, that's a really interesting and good question. The answer is a very difficult one to provide, but what we do know is that individuals who are in withdrawal from drugs tend to have reduced levels of serotonin in key parts of the brain, where the other transmitter I mentioned earlier, dopamine, is also important. And so there is a notion that one of the things that might cause you to take drugs again is an attempt to self-medicate, if you like, that lower level of serotonin in these key parts of the brain. So that might be an interesting mechanism. Clearly, serotonin is very closely linked to mood change, and withdrawal-induced mood change is a really quite difficult, at least early problem for people trying to stay off drugs.
Thanks, Barry.
You are listening to The Naked Scientists. Now, we've got a new feature for the new year, and each term Cambridge University's Rising Stars project helps young researchers to tell the world about their work. And we've teamed up with a group of rising stars so that you can find out what the next generation of top scientists are up to. So, seeing as we've been talking about the brain this week, we thought we would start you off with a neuroscientist. And here's this week's rising star, and that's Hannah Critchlow.
What happens to our brains as we learn, remember, and forget? Are there any physical changes we can see? Can we develop new drugs to improve our memories and turn us all into know-it-alls? And how do you link taxi drivers, seahorses, and spines? The brain is the most complicated and active part of our body, accounting for just 2% of our total body mass, yet greedily consuming over 20% of our daily energy quota. The brain is only 1.5 kilograms. But for neuroscientists like myself, the brain presents the most enigmatic questions of the entire body. There are over 100 billion nerve cells in our brains, and each cell is connected with up to 10,000 others, communicating with each other like an intricately designed, and sometimes flawed, computer network system. And one brain region that I'm particularly interested in is the hippocampus, which is shaped like a seahorse from the Greek hippos, meaning horse, and campi, meaning curve. Research on the hippocampus has provided insight into its function. Hippocampi brain injury patients have problems with learning, spatial navigation, memory and planning, showing that this region is involved in these higher cognitive functions. And scientists at the University College London have found that London taxi drivers have substantially larger hippocampi than most people. It seems that by using their spatial navigation skills and memory, London cabbies exercise part of their hippocampi and increase its volume, in much the same way that physical exercise builds muscles. The biggest ever winning score on Mastermind? A cabbie. He must have packed an extremely large seahorse. Schizophrenic patients, in contrast, have smaller hippocampi volumes, and I'm interested in the reason why. New research has shown that schizophrenic patients have fewer connections between their nerve cells, thereby accounting for their smaller hippocampi. The majority of connectivity between brain cells occurs on structures called dendritic spines, which are minuscule, 1,500 times smaller than a pinhead. Dendritic spines extend from nerve cells like buds extending from a twig. New dendritic spines form as we learn, becoming stable, mature spines as we memorise. And schizophrenic patients have fewer dendritic spines than healthy individuals. This might also be why they show impairments in cognition. If you imagine an aerial shot of London with many different roads branching off between landmarks, this could be compared to a healthy functioning brain with high levels of connectivity. On the other hand, a schizophrenic patient's brain would resemble the less convoluted road system of a newer city with fewer connections. My investigations have shown that we could potentially improve the treatment of schizophrenia by designing new drugs which specifically cultivate dendritic spine formation. And as a byproduct of this, we may also uncover new ways of boosting memory power for students like myself. Heady implications.
And that is Hannah Critchlow, and that's the first in our series of Rising Stars. Next week we'll have another young researcher telling us all about their work.
We're now on The Naked Scientist. It's that time of the year when everyone's thinking, how many inches, extra feet, pounds, stone have I gained over Christmas? How am I going to get rid of it all? Well, we thought we'd take a look at the science of dieting, and we've invited Dr. Toni Steer. She's from the MRC Human Nutrition Research Lab. She's come and joined us to talk about the basis of dieting. Toni, what's a diet?
It's normally most people understand diet as something where you restrict your calories in order to actually lose weight. And I think therein lies the problem, is that by saying diet, you seem to imply that it's something that you're going to do temporarily. And then once you've lost the weight, you're then going to go back to what you were normally doing before. And I think that that's what most people understand diet to be.
So in other words, it's flawed from the start, because unless you're going for a long-term change, you're going to put yourself back in the situation that led to you being overweight in the first place, and therefore the weight will come back on.
Absolutely. I think people set themselves huge expectations of what their weight loss is going to be. There was a study in America which asked very overweight women how much body weight they'd like to lose. And most of them said they'd like to lose around a third of their body weight, which is a huge amount. And so we have this big expectation of weight loss, and that we're going to put, the years of weight gain right in kind of 6 weeks with this diet, this magic diet that we're going to lose loads of weight.
I blame the newspapers a little bit, because every summer, when summer season's coming, people are going to go on holiday. You see this crash diet, lose X amount of stone in 6 weeks so that you'll look great on the beach.
Oh, absolutely. People focus very much on the aesthetics of weight loss. So it's all about getting into your size 10 bikini. And what we really need to communicate a lot better is actually the health benefits of very modest weight loss. There was a very big study in America looking at people who were overweight and about to develop type 2 diabetes. And what they did was, over the course of about 3 or 4 years, they got them to lose or maintain a weight loss of around about 4 kilos. That's around about half a stone. And what they found was that, OK, they hadn't had a massive amount of weight loss, but they'd actually significantly reduce their risk of developing type 2 diabetes by up to 50%.
But we can tell people who are a bit chubby, your blood pressure's a bit on the high side. If you lose some weight, it'll come down, and it'll come down enough that we won't even have to give you drugs for high blood pressure. But even so, it doesn't really help, in my experience, that much.
It's incredibly difficult. We're living in an environment where there's readily available food 24 hours a day, 7 days a week. The environment is incredibly difficult for most people to manage. And so, yes, the individual can do a certain amount, but actually we need to look at some of the bigger issues around town planning and transport and those kinds of things.
To get people more active, because presumably that's the bottom line, isn't it? Because energy in equals energy out. And if we either cut down the energy in, or we increase the energy out in order to balance things out.
Ideally, you need to do both. So you need to look at both sides of the energy balance equation. You need to actually eat less and do more.
So if you could just give us a checkpoint plan as to what you would put on a healthy diet, or a good strategy to slim down after Christmas, what would you advise?
OK, key strategies for weight loss. First thing is start from where you are. Do a food diary, have a look at what you're really eating, have a look at some of your triggers for where you may be reaching for those extra calories, like the chocolate bars. Then you need to cut down your energy density, so that's looking at calories per bite. So energy dense foods tend to be those that are high in fat. So reducing high-fat foods, increasing your low energy density foods, which is your fruit and veg, your high-fibre foods, choosing low-fat dairy, and getting out of the chair and exercising more.
So presumably my colleague's strategy of just eating a cucumber for lunch, it's not doing very well.
If you try to make really drastic changes to your diet, it's really, really difficult to sustain those over the long term. Your dietary habits, if you think about it, have been built up, over years and decades. And to break those by just thinking, right, that's it, I'm going to eat cucumber for the next 6 weeks, it's just not realistic or sustainable.
Thank you very much. And maybe we'll return to that at the end and find out, how we can really do it. I've tried to lose weight at the moment. Anyway, now it's time to catch up with Diana O'Carroll, and this is the question of the week.
Hello and welcome to Question of the Week from the Naked Scientists. It's time to put those fairy lights away, so here's our knotty problem.
Hi, this is Francis Tapon, and I'm calling from San Francisco, and I've listened to the Naked Scientists while I was walking across America for 7 months, and I'm addicted to your show. I had a question, though, while I was walking, and it's about tangling wires, because I would put my MP3 player into a pocket, and every single time I pull it out, the wires are completely tangled up. In fact, they're so tangled, I couldn't even do it myself. My question is, why do wires get tangled?
Well, quite a few of you got in touch to answer this one. Bert Lattimore linked it to entropy and how things just tend to go from order to disorder. He also said that nature is I can't say that word. Danny from the Netherlands cited this as an unfortunate combination of string theory and chaos theory. And Brad Tittle said that we're not wrapping our wires up correctly. Instead, we're twisting them up like springs and generally making things worse. Here's our expert's opinion.
Hello, I'm Mike Pearson. I work for the University of Cambridge, the Millennium Mathematics Project. I hear that somebody has called in asking about the fact that their headphones get in a mess whenever they put them in the bag. This is one of those things that seems to happen rather more often than it should. It's kind of surprising what damage a mindless bag can do. There are many more tangled possibilities than there are untangled possibilities if you think of the wires in the bag. So, in a way, just picking one of those tangled states is quite improbable. But it doesn't really matter. Any old tangled state will do. So the probability that one of those tangled states appears when you put your hand into the bag to get your cables out is actually quite high. So really all we need is something that will allow those wires to move within the bag. We need them to pick up some energy from somewhere, and jiggling the headphones around is going to be exactly what you need in order to generate the randomness, the chaos that you need in order to create all these knots. And any old knot will do.
Wires get tangled up as there are more ways for them to become tangled than not. But why would scientists worry about such things?
An analogy that you might look at is the cells of our body. There's an enormous problem that they have keeping all the DNA that they have organized inside the nucleus. And you can think of the nucleus as being a tiny, tiny little bag. It's only about 20 microns big. And the DNA is a big, long string or wire about 3 meters long. And that's the equivalent, if you can imagine it, of having an iPod cable 30 kilometers long stuffed into a 20-centimeter bag. How this all happens is quite a problem, which has puzzled both biologists and mathematicians a lot.
Tangling wires is a problem for mathematicians, biologists, and anyone with headphones. Next week, I'll be untangling the mystery of the boomerang.
Hello, this is Anand. I'm calling from Colchester, and this is my question. I want to know how the boomerang works and what's the principle behind that.
And after that, it'll be time for a bicycle race.
My name's Jennifer, and I'm from Chicago. My bicycling club has been having a debate. All other things being equal, who goes downhill faster, a fat bicyclist or a skinny bicyclist?
So did Freddie Mercury get it right? And how can we be sure that curved bit of wood is always going to come back? Send your answers and new questions to questionoftheweek@thenakedscientist.com or have a look at our forum at www.thenakedscientist.com/forum.
So that's it. Wires tend to get tangled just because it's more likely than not. But if you wrap your wires up right the first time, you may like to heed this advice from our forum from Brad Tittle. And he says, if you pay attention to winding your wire and twist in the direction of the torque, preventing the torque from building up in the wire, it won't get tangled. And on the forum as well, Artanimus, I think that's it, said that also people like roadies are taught to twist their cables in the right way. And Paul on the forum said he's heard you should use a knitting technique called butterflying to stop your wires tangling. Now, I am an avid knitter. I haven't heard of this, but it could be to do with the way that you kind of make tiny little skeins of wool if you're doing lots and lots of, using lots of different colours. You sort of make a loop and wrap the wool around the middle. Maybe that's what he means. But anyway, why do boomerangs come back? And also the question, who would go faster downhill on a bicycle? A fat person or a thin one? If you have any ideas, just email us at questionoftheweek@thenakedscientist.com or go to www.thenakedscientist.com/forum.
We've heard from Jill Allen King about the radio wire tangling business, and she said she always winds her wires around her radio, and that always seems to work. The radio in the middle stops the tangles from starting in the first place.
That's what I do as well. Anyway, earlier we left Ben and Dave with Jai and Jack making plastic bag squids and blowing up some balloons, rubbing them on their heads. Now it's time to go back to them and find out what happens.
Welcome back to Kitchen Science. We're still at Steward's School with Jai and Jack, and we've each got a sausage-shaped balloon and what we've called a plastic bag squid. Now, this is a little sort of tassel of plastic bag with lots of long, thin bits all attached together at the top, and it does really look like a jellyfish or a squid. What we told you to do before we went away was to rub them both on your hair to get them all charged up, and then hold the balloon with the charged side up and throw the squid in the air and see if you can catch it above it. So, do you want to have a go at rubbing the balloon on your hair?
Yes.
OK, and while you're doing that, don't forget you also need to rub the squid on the other side of your head. Now, Dave, I see you've opted to do this on your legs instead of your head. Any particular reason?
I think my head hair is a bit long, so it doesn't work very well, but my leg hair works beautifully when charging things up.
And how long do you need to do this for?
Yeah, just 20, 30 seconds will be plenty.
OK, so are we all ready? Everything charged? Now, as Dave said, what you need to do is make sure you remember which side of the balloon is charged, then throw your squid up into the air and see if you can catch it on the top of the balloon. OK, you ready to go?
Yep.
1, 2, 3...
Whoa, it's levitating above his balloon.
Dave has managed to catch the squid floating in the air. It now looks more like a dandelion seed floating in the air than it does a squid. It's almost a foot off the top of the balloon, so it's not actually touching. What do you think's going on there, Jack?
It's just floating. It's not doing anything.
So, Dave, you've done it. You've managed to make our plastic bag squid levitate. But what's actually happening here?
When you rub either the balloon or the squid on your hair, it actually transfers electrons from your hair onto the balloon or the squid. So they both become negatively charged. Negatively charged things repel each other. So they're going to try and push apart from each other. So when you balance the balloon below the squid, it's going to push it upwards and it'll float.
So the like charges in the squid and the balloon repel each other, and if you're quite careful with the balance, you can actually catch the squid about a foot above the balloon and keep it floating there.
Electrostatic forces like this are incredibly strong, so even only a tiny charge can make something fly like this.
Well, Jai, you said you thought this might be to do with static electricity. Are you impressed?
Yes, very much.
Jack, what do you think?
It's an excellent idea, yeah. It's really good to try at home.
So, Dave, do we see this effect anywhere other than a really cool party trick?
On a really small scale, it's one of the reasons why milk doesn't separate out very quickly.
So milk could separate into a fatty layer and a watery layer, but it doesn't?
Or not very quickly, yeah. That's because the little tiny droplets of fat have all got negative charge on the outside, so they repel each other, so they don't stick together very quickly, so it stays as milk.
Fantastic. Well, I hope you tried that out at home. But that's all for Kitchen Science this week. So it's goodbye from me, it's goodbye from Dave.
Goodbye.
And it's goodbye from Jai and Jack.
Goodbye.
Oh, thanks, Ben. And next week, Dave will be in the studio for a live Kitchen Science. What will happen? Until then, there are plenty more experiments for you to try at home on our website, and go to www.thenakedscientist.com/kitchen science.
Kat, I've got a question here from Emily Seward. She sent this in before Christmas, and we're a bit busy on the last programme. There wasn't time to squeeze it in, so I'm going to ask you now. She says, what is ageing? Is it caused by cumulative damage to cells as a result of everyday life, or is it genetically programmed? And if it is, can we prevent it with, say, gene modification?
It's both. Several things. First thing is that all your cells are pretty much programmed to die because you have things called telomeres, and every time your cells multiply, the telomeres are like the ends on your shoelaces. They're the ends of your DNA. Every time your cells multiply, telomeres get a bit shorter until they get so short your cells can't really multiply properly anymore and they die. There's also some evidence that our cells age, and it's to do with the metabolism of our cells causing damage to our DNA. And also when your DNA gets too badly damaged through environmental things or through things that are intrinsic to your cells, then they also die. Could we modify it? There's lots of people looking into this, and things like chemicals that are found in red wine, all these antioxidant kind of things that might have some effect on reversing the metabolic side of it. And as far as telomeres go, you're talking pretty hardcore genetic engineering to change the length of someone's telomeres. But there's some interesting research going on about whether the general length of the telomeres in your cells is predetermined genetically, and whether that might make some people more or less prone to cancer. And there's research going on at the moment to find that out.
I hope they cure it within my lifetime, so to speak.
I don't know. I don't think I can put up with you for many more years, Chris. Anyway, I've got a quick question for you. This is a question from Philip Chu in the US, and he says he's got a question about vitamin C. Some scientists seem to believe that it's the panacea for everything, and other scientists believe that the effects of vitamin C, I'm presuming this is large doses, are negligible. What's the general scientific gist on it?
Well, Linus Pauling, who got the Nobel Prize in biochemistry, used to take megadoses of vitamin C, and he did live to be in his 90s, but then so do lots of people who don't take megadoses of vitamin C. People have done clinical trials on this to see if taking vitamin C does translate into better health. The evidence is if you are vitamin C deficient and you get scurvy, that's very bad, but you don't need very, very much vitamin C in order not to get scurvy, and scurvy is incredibly rare in the population now, so warding off scurvy is probably not a good enough reason to want to take megadoses of vitamin C. In terms of warding off coughs and colds and things, there have been a number of trials, and the only one that really showed any major benefit was in Scandinavian cross-country skiers who took big doses of vitamin C. They found that with severe exercise, they were slightly lower risk of catching a virus or viral infection of some kind if they took the vitamin C compared with when they didn't. So probably because you're exposed to harsh conditions, cold air, your airways are getting very dried out, perhaps the vitamin C helps to ward off the damage to your airways caused by those conditions and therefore reduces the risk of the airways becoming vulnerable to viral attack. But under normal circumstances, I haven't found any evidence that people are better protected if they take vitamin C.
And there was also a paper, I think, about a year or so ago that showed actually if you take vitamin supplements, you're more likely to die. So
well, there was one showing that vitamin E, because everyone put themselves on vitamin E thinking because this dissolves in fat, perhaps it will reduce the rate at which arteries get clogged up by cholesterol, because when cholesterol is oxidised, it's more likely to block up arteries. So if you take something that dissolves in fats and hence is close to the cholesterol, vitamin E, perhaps that will stop it. And people who were on vitamin E started to have more heart attacks than people who weren't. So not very good news.
The Naked Scientists. For more information, get online at nakedscientists.com.
I've got a question here from Michael Stevens, and he says, I've heard on one of your podcasts about sunburn and the damage it imparts, but I was wondering, what's the actual cause of the redness in sunburn? That is, what specific damage to the skin causes the redness that remains over days after the initial UV exposure? In other words, what are we seeing that is happening at the molecular level that's red when you get sunburn?
Well, basically what's happening is inflammation. When you get sunburn, the ultraviolet rays from the sun come in, damage the DNA in your skin, and if they damage it really severely, then your skin cells will die in order to basically protect you from cancer because your DNA is damaged. And dying cells attract the immune system. They attract immune cells and things like macrophages that have to come in and eat up the dead cells, and that encourages inflammation. So you've got all these molecules called cytokines being produced, you've got inflammation, redness, you may notice swelling as well. If you get really sunburnt, you'll actually be a bit swollen, and that's what's going on.
So if it's down to inflammation, will anti-inflammatories like aspirin, for instance, make you feel better if you got sunburn?
They'll certainly help to relieve the pain. They may help to take the inflammation down. But of course, the most sensible thing is don't get sunburn in the first place.
You heard it there from Kat Arney, don't get sunburnt. A bit hard in this country at the moment. It was a bit hard in this country any time, I should think, but...
You'd be surprised. It doesn't take a lot of sun to get sunburnt, even in the UK.
What about, just as an aside, Kat, what about sunbeds, though? Because they're a bit serious, aren't they? I was reading a statistic the other day. It's a totally unregulated industry. In one case, there was a set of sunbeds that people were testing, finding that the intensity of the UV was 5 times stronger than you'd get from the noonday sun on an Australian beach.
I know, and that's a very interesting issue. And in fact, in Scotland this week, in the Parliament there, they're having a debate about whether the sunbed industry should be regulated, and particularly as well whether sunbeds should be banned for people under the age of 18, because at that age your skin is really very sensitive to this kind of damage from the sunlight and also from the ultraviolet radiation in sunbeds. But yes, at the moment, particularly in the UK, sunbeds are pretty much unregulated. There's a voluntary code of conduct from the Sunbed Association that sunbed parlours can sign up to, but it's not compulsory.
So they could be harmful. You could actually be doing yourself quite a lot of damage because they haven't actually been standardised what dose you're getting and what it's doing to you.
Absolutely. I mean, we'd recommend people to steer clear from sunbeds generally, and especially using them excessively. And, do watch out, because they are damaging your skin. And if you overdo it, you are increasing your risk of skin cancer.
And you will end up looking like a prune. Thanks, Kat. Right, well, that's all we've got time for this week. Join us next week for our question and answer show. It's the Science Phone-In. You just send in your questions and we'll try and answer them for you. Chris@thenakedscientist.com is the address to send them into. Other highlights of that programme, we'll be finding out what's been happening in the chemical world with Chemistry World editor Mark Peplow, and also our tech correspondent Chris Vallance will be joining us to bring us up to speed with what kinds of gadgets you should have got for Christmas if you didn't. Thanks very much for joining us. Been a great pleasure having you, and a big thank you to our production team as well. They are Ben Valsler, Mira Sinthalingham, Dave Ansell and Diana O'Carroll, and our guests this week, Leslie Jacobson, Julie Cower, Barry Everett and Tony Steer. Don't forget, all this show and its content ends up on our website, nakedscientist.com, and there's a great forum there which is a thriving hub of science interactivity, and that's at nakedscientist.com/forum if you'd like to join us. Bye-bye.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.